Okay, so in this video, let's talk about the transgeometric complexes and crystal field theory. So the crystal field theory is the most important thing when it comes to the complexes. Before we are moving into the complexes, we need to understand this crystal field theory very well. So let's move on to crystal field theory. Crystal field theory. This theory explains two main effects, or we can say two main observations in complexes, right? The first thing is how these complexes show colors. We can explain this using a crystal field theory, and also the magnetic properties. As like the most theories, we have assumptions for this crystal field theory too. The first and most important assumption is every interaction, every bond we considered as, right, every bond we considered that electrostatic interactions. And secondly, we consider that ligands or charges or metal center, everything as points. They do not take any volume in our space. They are just points. That's our assumption. So you need to have a basic idea of these two assumptions, and then let's move in. So if we have a complex like metal center, right? If we have a metal center like copper 2 plus, let's say copper 2 plus, this metal or copper is d block element. This is a d block element. So why do we say d block element? Because it contains d orbitals. There are a total of 5 d orbitals. If you know how we can label these 5d orbitals, it's very good. If you do not know, it's completely fine. I will explain you everything. So here first we have dxy, dyz, dzx, dx squared minus y squared, and dz squared. These are the 5d orbitals we find in a metal center or in a d orbitals. So the main thing or the important thing is you need to have a very good idea how these 5 orbitals presents in our three-dimensional space. So let me show you that. The picture in the right side, this picture we do not need it for now. Let's move in here. So here this is the dyz orbital. This is the dyz orbital. As you can see, as the name suggests, it's on the yz plane. Here y, here z. This is the yz plane. The orbital is in the yz plane, and the main thing, it is in between the axes. Here, like this is the x-axis, right? Don't confuse, right? Like this x is coming out of your screen, right? Coming out of the plane. So these orbitals are in the zy plane. So these 4 orbitals, I mean like this orbital, this dyz orbital is not on any axes. They are in between the y and z axes. Same like the xz orbital. The xz orbital is in the x and z plane, which in between the x and z axes. Same dxy orbital, it's on the xy plane and between the x and y axes. These two orbitals are the left one, dx squared minus y squared and dz squared. Here this is very important. Dx squared minus y squared is on the axes, right? Here this is on the x and y axes. This z squared is on the z axis. That's an important thing. So you need to have a very good idea about these 5 orbitals. You just need to understand that how these 3 orbitals presents in a space, and this how these 2 are on the axes on themselves. So In this video, let's continue our talk in octahedral complexes, because they are the easy thing or the basic things to explain complexes. Let's take example like CuH2O 6 times 2 plus, right? So here, if I consider this complex as this one in this picture, here in the gray color we see our copper 2 plus, right? And here in the green color we have H2O. So when I'm going to create this complex, first I need copper 2 plus ion. You know the copper 2 plus is a d block element and it has 5 d orbitals. At the first, before any contacts with the ligand itself, when the copper 2 plus in environment without any ligands, without any interference, when it's on a free ion, all these 5 orbitals are having same energies. But as you can see, when the ligands are binds with the metal center, when the complex is formed, there are bonds here. There are bonds. If I show you the axes like this one, x, y, z axes on this particular complex, this is going to be the x-axis, this is going to be the y-axis, and this is going to be the z-axis. And here you can see a very special thing, right? So when the bonds are forming, there are 2 orbitals which are going to overlap these bonds, these newly formed bonds between the metal center and the ligands are going to overlap with the 2 particular d orbitals. Which are they? dxy, sorry, let's take a good color. Okay. dxy, dxz, dyz, both, all these 3 orbitals are in between the axes, right? But as you can see in the picture, these newly formed bonds between the metal center and the ligands are all in the axes. So there are no interactions between the dxy, dxz and dyz orbitals with these bonds. But these two orbitals, they are going to overlap with these bonds. So as I have told you in the beginning, all these bonds are electrostatic interactions. So when these bonds are forming, these orbitals will become much unstable because of the electron-electron repulsions. What is meant by the unstable? They are going to increase their energies into higher levels because they are unstable. But these three, they are not gonna that much affected by the ligand, so they are gonna stay in the lower energy. So you need to understand this thing. So let me give a clear idea. So here, when we are talking about the energy diagram, here we have the energy. At first, when the copper 2 plus ion in its free form, we have 5 orbitals in the same energy. Now when we have put the ligands and the metal ions together, first the more interaction will be built, so our whole 5d orbitals will increase their energies due to that electron-electron repulsion, and then start the deviation, which 2 orbitals which becomes higher because due to their unstability. If I ask which orbitals, they should dx squared or my dx squared minus 5 squared and dz squared. And there are 3 orbitals which are dxy, dxz and dyz. We call this orbitals as T2G orbitals and this orbitals as UG orbitals. So there are some small things you need to understand about this particular energy diagram. If I right, so this whole gap over here up to this whole gap we denote this as delta O, which we call as crystal field splitting parameter. Splitting parameter. Crystal field splitting parameter. And this part, this gap over here, from our baseline to the UG orbitals, it is valued as 3 over 5 delta O. This is plus value. And this bottom gap is 2 over 5 delta O. These values are important, right? These values are important. In some books, you can see, in some books, this delta naught is referred as 10 dq. Both are the same, right? Both are the same. This is one parameter, this is another parameter. That's the only difference. Both are the same. You need to understand, what you need to understand in here is that this crystal field splitting parameter is based on several factors. It can based on the metal center, it can based on the ligand, it can based on the environment, chemical environment, temperature, likewise. This depends. So this is the main thing. This deviation is the main thing you need to understand in an octahedral geometry. This chart only applies to the octahedral geometry, right? The other geometries like tetrahedral ones and other stuff, this won't apply. So this only applied for the octahedral geometry. And let's move into another small thing, very small theory part, which we call as crystal field stabilization energy. Crystal field stabilization energy, right? I will explain it by a simple example. Let's take vanadium 2 plus. Let's say that vanadium 2 plus has created a complex. So what is the vanadium's electron configuration? It is like 3s2, sorry, 4s2, 4s2, 3d3. I hope I'm right. Right? I hope I am right. Yeah, I'm right. Okay. So this is not vanadium. This is not vanadium. This is vanadium 2 plus, which means 2 electrons have been removed, which means only 3d3 electrons are present in our complex. So now I'm going to put these 3 electrons into our diagram. So you know we need to start from the lowest energy level. This is the lowest energy level. Now this term crystal field stabilization energy, we can find this energy by the number of electrons. Here, as you can see, we have 3 electrons in T2G level. What's the energy gap or the energy value for T2G parameter? T2G energy level, this one. Yep. Minus 205 delta naught. So the crystal field stabilization energy gonna be 3 over minus 2 over 5 delta naught. This 3 is due to there are 3 electrons. So we can have the answer minus 6 over 5 delta naught. So this is the crystal field stabilization energy for vanadium 2 plus complex, right? This delta O may depends. Delta O, this delta O contains a value that specifically for each complex. When the vanadium changes the ligand, this delta O changes. So let's do another example. Let's assume our electron configuration of a metal ion is like this. right? So let's assume like we have a configuration like d5 configuration. So there are 5 electrons to put here, 1 2 3. Let's put the other two on here. Yes, now there is a chance that there is a possibility we can put these 2 electrons into here too, like so. We will talk about that point in the next video. Just for now, let's consider a situation like this. Now if we are asked to crystal field stabilization energy, how you can find it? There are two levels now, T2G level and EG level. So this is not UG, right? It's EG. I'm sorry, I am mistaken. It's EG. There are two levels, T2G and EG level. So first, let's calculate the T2G level. There are 3 electrons, minus 2 over 5 delta O, plus the other level, EG level. There are 2 electrons with 3 over 5 delta O. So we can calculate both these two, minus 6 over 5 delta O plus 6 over 5 delta O, which equals to 0. So the crystal field stabilization energy is going to be 0. This is the simple structure. So I hope you got something about it. We are going to talk about the strong field and weak field and magnetic properties in our next video.